Hey, so there was one last thing I was going to mention in the review of physics, but here is my dog Lenny. He got a little tired and wanted to go to bed, and I was just about finished. By the way, so this is the official bonus 2 a.m. lecture video here. I've managed to go all the way until 2 a.m. in the night, and so there was one last tidbit I was going to mention here. And so this is just for those of you guys who want a little bit more enrichment and or want to watch a dog. Let's see. Here we go. So there's Lenny. Come on, boy. Actually, that's kind of how he does his thing. So anyway, there you go, buddy. So the last bit that we talked about there in talking about kind of how particles, or about just how any object that's rotating has some sort of like not only angular momentum, but like an angular momentum direction. He's either really interested or really angry at me. I don't know which of the two. But as an object spins around, for example, it has some inherent angular momentum. And the really cool thing that we've kind of learned is that, and as you guys will see as we go through the calculations of quantum mechanics, particles inherently have some sort of angular momentum, which we associate with a spin. We say that, hey, if they were to spin that way, they would have an angular momentum pointing up or down. The same way, according to that, like the right-hand rule that we just talked about. And sorry, so it is apparently kind of an inherent property of the universe. And so one of the things I didn't mention, but I think is important to say, is that we had talked about previously. We looked at the conservation of energy. We talked about the conservation of momentum. The third conserved quantity is conservation of angular momentum. And so, for example, and the reason why this is super important for not quantum mechanics, the solar system or astrophysics, is that the way that we think our solar system worked is that the way it formed, and if I wasn't sitting on my dog's bed, I would actually like demonstrate this. But we believe that our gas, the cloud of gas and dust that originally our solar system formed out of, was just this huge like swarm of molecular hydrogen, and mostly hydrogen, a little bit of helium, tiny bits of other stuff that we're now made of, but literally like thousands of light years across, and just wide and very sparsely populated. But what happened over time? Parts of it clumped together, and this is where the fun started, because as those clumps started to like accumulate, they started to gain more mass and therefore more gravity, and they pulled themselves together. But as they pulled themselves together, what happened was, and as you recall, their moment of inertia decreased. So I hope you see what's going to happen here. Now, that big, huge molecular cloud, we actually believe was the result of a supernova that probably happened, we're guessing about maybe 7 billion years ago or so. Our sun's about 4.5, 5 billion years. Now, we clearly can't go back in time, but we know that something caused the region of our galaxy to like kind of really start to implode on itself. And there was like literally hundreds of other stars that formed along with us, because these pockets of gas condensed. And as they condensed, the whole cloud was very slightly spinning the whole way around. I mean, literally, that's just what happens in the universe. Angular momentum is conserved. Stuff spins, is what it is. And our galaxy, we know, is very slowly spinning. It goes around about once every 200 million years. So that means that since our sun was born, it's gone around 5 times every billion years. So it's gone around the Milky Way roughly about 20 times. And so we understand now, though, that like any gas clouds that form in the Milky Way have that same intrinsic spin. And so essentially that's why the gas molecules and the dust molecules that eventually coalesced into our sun and the solar system, that's why eventually, or why initially they even have even a slight amount of spin. And therefore, this is where the physics comes back in. As gravity decreased their moment of inertia, remember, angular momentum, which is conserved, L, I think it's right, maybe it's like that for you guys, L, the angular momentum is the product of moment of inertia times angular velocity, I omega. By the way, omega is not W. Never call it W, don't write it as W. Neither is alpha fishy. Exactly as bad. So anyway, moment of inertia is I omega. as I goes down, omega has to go up. And that's exactly why our solar system began spinning in unison. The big, huge gas cloud, before we ever had a sun, before we ever had a planet, literally the huge cloud of gas was all spinning in the same direction, just simply because as something begins to contract, in order to conserve angular momentum, it has to spin up. And then the cool stuff that happened after that was now that cloud of gas, kind of the same way that as you throw like a pancake up in the air, no, well, maybe you throw pancakes in there. What I meant to say though is a pizza ball in there, like a ball of pizza dough, as you spin it, it tends to flatten out. And that's what happened to the gas in our solar system. Just simply due to random thermal collisions between molecules, it flattened out as it spun faster. And now we see, and then very gradually, the pockets of gas that were slightly denser, the clumps that started forming, started to pull more, and those became planets. The main central part, the densest part, the heaviest part, the part that like accumulated the most stuff is clearly now our sun. It's 99.99% all of the mass of our entire solar system. I mean, like literally, like everything else is in the hundredths of percents. And then so the main center part of the sun, the clumps that initially formed, that gradually accumulated more crap, that became the planets. And then some of those planets even started to like grab some of that other unclaimed debris, which are now the moons of, for example, like, you know, the terrestrial worlds, Earth, Venus, Jupiter, Earth, Venus, Mars, Mercury. We have few, if any, moons. The Jovian worlds have literally dozens, like Jupiter has 60 some. So those Jovian worlds accumulated all of that unclaimed debris. And then when the sun finally like gravitationally coalesced, and when its density and its thermal temperature became so high, it began fusing. Then it sent out this debris of just, you know, like, I mean, it's a solar wind, but it was just a big belch, basically. It sent a big burst of basically matter and radiation and pressure, which cleared out the rest of the solar system. And now what we have are mainly just the big rocky bodies which survived that last gasp that the sun spit out. So that's why angular momentum is so important for this whole thing. I think it's really cool. All right, so that's our 2 a.m. chat here. Maybe we'll have more of these. I hope not to go into 2 a.m. for lectures the rest of the semester though. So anyway, hope that's fun. And we'll go on to some more stuff, the electromagnetism later on. So cool.